Let's imagine here a simple experiment that we have a particle of which spin is conserved. So indeed we consider a particle of which spin is conserved, and it's equals to 0. After a while, particle actually decays to two different particles, and let's assume also that the two particles can have different spins that can be spin 1 or 1, or it can be of spin -1 or spin +1. So we can still see that any combination you take, for example, this or this combination of the final particles, you will still get a spin 0. And so right now we'll have a superposition of two particles, and this is what entanglement actually is. So before it's some sort of a superposition of two particles. It's interesting also that entanglement, not every superposition is entanglement, but every entanglement is a superposition of the state, and that's a notation that we use in quantum mechanics to present actually the entanglement of two states and what does mean when the particles are entangled. So Einstein spoke about the spooky action distance. It means that when you actually perform a measurement on one particle, you would measure also, for example, another particle at the same time. So it means that even if you separate, for example, two quantum particles that are entangled at very high distances, performing measurement on one would also make the measurement on another. So you would know the state of another particle. And yes, it's interesting that when all the systems, for example, quantum mechanics, they very superposition, like quantum mechanical systems, they got really very easily entangled with the environment itself, and this process we call decoherence. Yes, so